We have a 0.5 kilogram ball tied to a 1 meter long string, and it's swung in a vertical circle at the velocity of 4 meters per second. To find the tension in the string, what we're going to do first is to draw a diagram. So we have this ball. Ooh, awful circle, Mrs. Weber. So we have this circle, and we have a ball, and then it's attached to a 1 meter string. And from the center here, this 1 meter string is going around in a circular motion, okay? The velocity is 4 meters per second. So the issue is that the tension actually is not the same in the whole circle, because remember, when we're at the bottom, it's going to feel heavier because you have your tension force working to make your acceleration point inward, and then you also have your weight force. But up top here, we have both the tension and the weight force working down. So what we're going to do is we are going to determine the tension of the string at both locations. So for the tension at the bottom, when I look here, so this is the free body diagram I'm going to be drawing. When I look here, I know I have the tension of the string, all right, that force is up, and I know the weight force is working downward. So if I'm trying to find the sum of the forces at the bottom, I know that my centripetal acceleration is inward, and therefore my net force has to be up. So for the bottom, I know that the net force is in the upward direction. Well, if that's the case, then my tension is a positive force, and the weight force is a negative force. And because this is centripetal acceleration, I know that it's going to be mv squared over r. So then all we have to do to solve for t is add these guys together. So we do some plug and chug. And then plug that all in, and you should get about 13 newtons. Okay, so same rock, but this time we're going to look at when it is at the top of the circle. So again, the radius is still here, and the radius is still 1 meter. Speed is the same. Okay, but the difference is, if you take a look here, if this is the string, well, the force causing the centripetal acceleration is now inward. So when we draw the free body diagram, it is going to look a little bit different because we have the rock here, and we have the tension force working towards the center of the circle, and we have the weight force towards the center of the circle, okay? And this time, the net force, for it to be toward the center of the circle, the positive net force is down. So these are both positive forces. So when we find the sum of the forces, we'll go T top. When we find the sum of the forces for the top, we are adding these two forces, the tension force and the weight force. So T plus mg. And again, that's centripetal, so we know the sum of the forces is mass times acceleration, which is mv squared over r. So to solve for tension, we have mv squared over r minus mg. So we have T equals, we plug in everything, so again, 0.5 kilograms times 4 meters per second. We're going to square the velocity, and that's over 1 meter. And then minus 0.5 kilograms times the acceleration due to gravity. So when we plug this in, we end up getting 3 newtons. And then what this tells me is that during the rotation, all right, so during the rotation of this ball swinging around in a circle, I know that the tension is in between 3 newtons and 13 newtons. So at the bottom, it is going to have the strongest tension, right? So that's at the bottom. And the smallest tension it's going to have is at the top. So we can have all these values in between depending on where your rock is located. All right, it's always going to be in between these two max tension values.